And you are of course most welcome. This is Project Euler problem number 21, amicable numbers. So the proper divisors of 220 are this list of numbers here, and if you add them up you get 284. So imagine this as a function. You input the number 220, you find all its proper divisors, and the output is 284. Now let's take 284 as the input and run the function again. We find the output is 220, so it's vice versa. The input to the output of one function is the input to the other, or something like that. But you can see what we're getting at. Anyway, evaluate the sum of all the amicable numbers under 10,000. So there are many ways to skin this particular cat. I've chosen two. One which looks very impressive but is actually incredibly slow, and one that is a bit more a bit uglier but more elegant, if that makes sense. Anyway, let's have a look. This is the I'm actually going to take this window away because I'm going to need to. Yeah, it's going to need to happen today. So the first way to do this, I set myself a challenge. Can I solve this problem in, what's the lowest amount of lines of code I can use to solve this problem? I got it down to either 3 or 4, depending on whether you count the function definition as a third line or a fourth line. Anyway, so this is a brute force method. It's just going to take every number from 1 to 10,000, find the sum of divisors for each number, and then find the amicable pairs. So it goes something like this. I do want to import the time first, so from time import perf counter. I've been told that perf counter is more accurate than just time, so we're going to use this today. So start equals perf underscore counter. This of course does not count towards the 4 lines of code. 4 lines of code begin now, so we want a function to get the sum of proper divisors for every number. So def get sum of proper divisors. I'm going to shorten this just to get sum, because otherwise the code's going to look quite messy. So get sum. Now we're going to use list comprehension for this. So return sum I for I in range. So we're going to go from 1 up to half of n, because that's where all the divisors are going to be. So n divided by 2 plus 1, because Python is bloody awkward. We have to put this plus 1. I don't know why. If n mod I is equal to 0. So we just count up from 1 up to half of n, and if I divides by n, then it's a divisor and we add it to the total. So that is all we have for that one. Then we need an array to store the divisor sums for each integer. So I'm going to call it D, and you'll see why later. Very short name. This is another list comprehension. So get sum I for I in range, and we're going from 0 up to 10,000, and that's it for that one. So we've got the array with the sum of divisors for every integer from 0 up to 9999. Now we've got to find the amicable pairs. So this is a very long line of code. So we're going to print it off. We're going to print a sum. It's going to be I for I in... Oh, no, that needs to be inside a list. There we are. I for I in range. So this goes from 0 up to 10,000. Now this is the bit that I find really hard to explain. Just trust me, it works. So if di is less than 10,000. Now, this is important because if you have a number like, say, I don't know, 6192, which I imagine to be a very factorable number, it might have a divisor sum of, say, 10,002. I don't know if that's true. It might. But then we've got to use that as the input to the function, and of course this array only goes up to 10,000, so it will throw an array index out of bounds error. So this is the first check, and di is equal to I, and di is not equal to I, because there are some numbers like let's think of an example, 6 for example, which is which would be an amicable pair to itself, because 6 has 6. When you add up its proper divisors 1, 2 and 3, you get 6. So that would come up as an amicable pair in this algorithm unless I put in this line of code. So it should actually be not equal to. There we go. That is, oh, we're almost there. I think there's one bit missing. I think it's that. Nope, wrong place. I think it might be that. Nope, I've got this in the wrong place entirely. Let me see. di is not equal to I. That's correct. That's correct. That's correct. Oh, what are you doing there? You're in the wrong place. Get out there. That should go away. Right, that's fine. So, can you see all that? Yes, you can. So right at the end, I'm just going to do... oh, I can't use perf counter. I'm just going to use time. Right. From time import time, this doesn't matter that much. They're not that different. So s equals time. And then right at the end here, we want to do time minus s. Right, let's run that. Taking a while, so that does produce the correct answer, but it took 4 seconds. I'll just run that again to make absolutely sure. Sometimes on the first run it can take 3.96. Try again. On the first couple of runs it can take a little while, then it speeds up. Yeah, it's roughly the same, 3.78. So, if you want to impress someone who doesn't know very much about computer science, you could use this. It's not very readable, but it'll make you look like you really know your stuff. If someone does know their computer science, then you'll just get laughed out of the room, because this is very slow and basically brute force. So now I'm going to show you a much better way to do this. Okay, I was feeling a little bit extravagant, so I've got it down to 2 lines of code. I'm just going to see if it works. So yes, it does. That's perfect. So yeah, 2 lines of code. That's yeah, it's alright. It's still shit though. Okay, so now let's work on an algorithm that isn't objectively terrible. So I've written down the numbers 1 to 20, and we're going to find their proper divisors using an efficient algorithm. The problem with the previous method is that it involved a lot of repeated calculations. So for example, 36, once you found the divisors for 18, well, the divisors for 36 are just the divisors for 18 plus 18. So we didn't need to do all those calculations again. This algorithm removes all those calculations and does it a lot quicker. So here's how we do it. Start with 1, and we find every number in our set that divides by 1, which is all of them, and we add 1 to the sum of divisors. So 1, 1, 1, 1, 1, 1. I should have started with this actually. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. There we go. Right. Now we go to 2 and we repeat the process. So add 2 to every number that has 2 as a proper divisor. So that goes to 3, 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 and finally that goes to 3. Next, we do the 3's. So that goes to 6, this goes to 4, that goes to 6, that goes to 4, that goes to 6, and we're done. Now the 4's. So that would be 8, so that's there. That goes to 7, 12 goes to 10, 16 goes to 7, and 20 goes to 7. Okay. Then the next one we do is 5, and do that again. So yep, 3, 10 goes to 8, 15 goes to 9, and 20 goes to 12. Now we do 6. So that's simply 12. So that goes to 16, and 18 goes to 12. 7. 7 goes 14, so we add 7 there, that goes to 10, and that's done. 8, 16, so that goes to 15. 9 is 18, so that goes to 21. And 10 goes to 20, and that becomes 22. And that is a much more efficient way of finding the sum of divisors for all numbers. So, as you can see, we have prime numbers, so 3 has a sum of divisors of 1, so does 5, does 7, 11, 13, 17 and 19. So, that is roughly how we are going to tackle this problem. I'll just go and get a drink and then we will have a bash. Right, then I've had my drink, so let's have a bash. So I'm using time from time import time again. I know perf time is preferable, but since I used it last time, I want to be fair and use it again this time. So start equals time. Right. So we need an array of integers from 1 to 10,000, all of them initially set to 1. So d equals 1 times 10,000. That'll just cut down a bit on processing time. We know that every number from 2 up to 10,000 has 1 as a proper divisor, so no need to loop through those. We will just set d0 and d1 to 0, just as if we were doing the sieve of Eratosthenes. So for I in range, we start at 2 and we work our way up to half of n, which in this case is 5,000. Of course Python goes one step beyond because it's bloody awkward. Then for j in range, now j starts at 2 times I, and it goes up to 10,000. But it goes up in steps of I, so there we go. And then we simply, if, I've written down here if I is not equal to j, but I is guaranteed not to be equal to j, so you can skip that. Yes, I do work from notes, I have worked this algorithm out. So dj plus equals I, and that should get us the correct score. So I'll just do print D220. Since we already know D220 and D284, I'm not giving anything away. So I'll just check they're correct. Yes, they work, so that's cool. Right, that's that done. Now we do the second part of the algorithm, which is to find the amicable pairs. So we need a total, so sum of amicable pairs. I might as well use a meaningful variable name at some point, but I promise not to make a habit of it. For I in range 2 up to 10,000. Okay, so if obviously if again if the sum of divisors is over 10,000, then its index won't exist in our array, so we skip it. So if di is greater than 10,000, then skip it. In all other cases, and again, I promise you this code does make sense. Sum of amicable. So if we have an amicable pair, then sum of amicable pairs plus equals I. That should work. So print sum of amicable pairs and then time minus start, and that should do it. So reminder, under the old algorithm it took just under 4 seconds. In this algorithm it will take 0.029 seconds. So that is it for today, and I'll look forward to seeing you again for, well, I don't know about actually see you, but I'll see you for problem number 22. Thank you for watching.